let's get started. The correction from last time. So now we talk about so please be careful about your foot. Please do not kick if you sit in the front. So we talk about the scalar theory and final propagator. So final propagator is just time ordering two-point function, and we know that for time ordering two-point function we need to be a bit careful of sign and so on. So for x naught is greater than y naught, and the y naught is greater than x naught, the integral, the content integral is slightly different. So here you have the plus sign here. On the other hand, you have a negative sign, which means that the forward in time you have to e to the minus ip. On the other hand, if you go backward in time, you have to have a e to the plus ip. And then last time my explanation was correct in this term, but the second term I've missed one explanation. So from second to third, I need to in here the second term. I do the following transformation: p goes to minus p. This part I didn't explain last time. So here you have e to the plus I. So here e to the plus I p dot x minus y. Therefore this should be e to the I p naught x naught y naught minus I p, and special time is negative sign. However, you can take transformation from p to minus p, then it becomes plus. That's why it comes the overall factor e to the I times p vector and then x minus y, okay, in the special inner product. And you can just take it out because here you also have minus sign, so which means this is plus sign. And then time component, you just have a sign difference, okay, sign difference. And of course, you have to be careful. So if you do that dp 2 pi minus infinity to infinity, if you take the transformation p goes to minus p, then we have the infinity minus infinity to infinity dp 2 pi. But if you so minus sign cancel with swapping the order of the integral, this is infinity minus infinity dp 2 pi. So integral measure does not change. Okay. So only the change is minus and the plus here. And if you take the contour here, the P0 integral so as I mentioned last time, so I will only focus on the second term because the first term the explanation was correct last time. So the second term, infinity minus infinity P0 2 pi p square minus m square over I e to the minus ip dot x minus y. Is it hard to see from the back? Is it okay? Is it okay? And then this can be understood as the so dp0 2 pi p0 minus ep and p0 plus ep over I times e to the minus ip dot x minus y. Okay. So we just go, I'm very sorry. I think I should write bigger. And also do the I times e to the I minus ip naught. Yeah, p naught and then x naught minus y naught. And this is also p naught, x naught, y naught. Okay. Okay, so this manipulate like this way. Okay, then, so the problem is this arc do not contribute, so we need to explain this arc does not contribute, that the, so if you take the P naught, so this is R, the radius R is big, R goes to infinity. So this part, imaginary part of P naught is positive, okay? It's positive, right? So if you plug it up into here, minus I cancels, so this is plus I, right? Plus I. Then you got plus sign here in the real part of this inner product. However, x0 minus y0 is negative because of this theta function. Okay? Always it's negative. Okay? So therefore, this one, once you take r goes to infinity, arc contribution decays exponentially. Okay? So therefore, arc does not contribute anymore. And then we pick the pole from here, minus EP, and be careful about sign. So if you plug in minus EP here, it becomes plus I times EP, x0 minus y0. This is exactly what we want here, right? Plus I EP, x0 minus y0. Okay? So therefore, we have a desired answer that this one is equal to 1/2 EP e to the I EP x0 minus 1. So this is exactly what we want. And then, yeah, the last time, so I didn't do this transformation, so my explanation was wrong. But I hope you understand why this arc does not contribute for seconds. The first part was correct. So if you forget about it, you can take a look at the video. I'll watch your video in the previous lecture. Any question at this moment? Okay, now then let me move on. So then a final propagator can be written as so if you incorporate this the time integral, time component of the momentum integral, this can be written as a full integral of a momentum space e to the minus I p dot x minus 1. So this is manifestly Lorentz invariant, but you have to be careful the contour, that this contour C should be taken as something like minus EP and for P0 integral. So that's what it means. And this contour really comes from physics. So for forward in time, you have to have an e to the minus IP. Backward in time, you have to have an e to the I times p plus. And then, so there's sometimes open. Physicists write like this way. You just push the pole, but the position of pole a little bit. Like this. Sorry, minus. By changing a little bit the pole. Okay. So you can just push the position of pole a little bit above and down by introducing epsilon. So that's called epsilon prescription. Anyway, so that's the open physicists use to get the integration on the real axis on P0 integral. Okay, so this is called Feynman propagator for scalar theory. So this is Feynman propagator. this is a free theory. A free theory means that the free theory means that the Lagrangian is something like, so we start with Lagrangian. It's a bit noisy outside. Okay. It only has a kinetic term with mass term. Okay. So there's no interaction term. There's no interaction term. So the particle just do not interact with the other particle. So if you just, I mean, we will learn. So we just so later we will learn Feynman diagram, and we just associate this. The particle just goes straight, and momentum p, and we associate this is I over p squared minus m squared. That's the what we are going to learn in subsequent lectures in Feynman propagator. I will explain later, so don't worry even if you don't understand it. Come on. Okay. So this Feynman propagator is the, in fact, green function. So this is function of Klein-Gordon theory. Klein-Gordon equation. Klein-Gordon equation. So which means as follows. So the Klein-Gordon equation is the, so this equation motion is something like a plus m squared. So this was the Lagrange equation or of this theory, it's Klein-Gordon equation. And just act this the operator on this Feynman propagator, and we'll see what's going to happen. So so if you act this one, then this is equal to, so the propagator is there, so therefore d for p 3 pi p squared minus m squared plus I epsilon in the denominator, and then so this derivative, two derivative acts on this exponential. So with the point, then what you get is that the minus p squared plus m squared e to the minus I p dot x minus 1. Okay. So this derivative only see x component over there. So you have ip dot minus ip dot minus ip, which is minus p squared. And of course, the numerator and denominator cancel. I mean, depends on the how you introduce a plus epsilon or not. And they cancel. What you get is something like minus I. So this is just we'll give you that function. So therefore, so this equation motion, if you act this plug in equation motion, Feynman propagator into the equation motion, you get their function. So this means that the Feynman propagator is just a green function of the Klein-Gordon equation. And in particular, if you add some source term perturbation, like plus j dot phi, into the action like this way, so it's called source term, the equation motion will change. The equation motion will change. Klein-Gordon equation will change like this way. Like this way. Then the equation the solution of this one is just can be written. Classical solution of this one. Classical solution of this one can be written as the follows. Even if it, so thanks to the Feynman propagator, if the let's act on, so the plug that one into here. So then what we have is that the classical is equal to I times d4y. But if you act this one on the Feynman propagator, we get the dot function there. So minus I dot 4 x minus y and jy. So therefore, you can just do the integral here. What we get is that you just get the j of x. So therefore, even if you add this source term of perturbation to the in the Lagrangian, classical solution can be obtained by just integral of Feynman propagator times source the current j. Do you understand? Is it okay? Okay. So therefore, this Feynman propagator is very, very, very important. Okay. Fine. Maybe I should explain it. Should I explain it? Okay, I think retarded and then advanced green function we're not going to use, so I'm not going to explain it. If you want, you can just take a look at it. So I would take non-relativistic limit. Or maybe I should explain. Yeah, I don't think it's meaningful to explain. So let's move on to non-relativistic. Okay, let's connect field theory and quantum mechanics. Okay, so most of you guys, I guess, they learn about the quantum mechanics. I hope so. So we now learning relativistic quantum field theory, and we want to connect by taking the non-relativistic limit. So non-relativistic limit is just the momentum, spatial momentum less than, much less than the mass. So therefore, the EP is equal to square root 1/2 is if we do the so this is equal to m square m plus p square to m dot dot. So if you go there, if you expand it by Fourier transformation, it becomes subleading. Okay. And suppose that the phi So the Klein-Gordon equation, we just look at it here. And so we know that it has a Klein-Gordon equation, but you just take a look at some component. So the e to the minus I mt phi of x. If you just write down the this is time t, and this is plus. If you just approximate the wave function to the following form and plug that one into the Klein-Gordon equation there, what you get is that the this Klein-Gordon equation means that the just do the ordinary calculation. I'm not going to derive everything. If you're careful, you just follow the calculation by yourself. So you get this kind of equation where the dot again means time derivative. And non-relativistic limit means that the phi dot double dot. Non-relativistic limit means that the phi double dot is much less than m phi dot. Okay. Therefore, this immediately implies that the I times so we can ignore this part because this is much less than this one. The amplitude is equal to minus lambda square to m phi. Do you understand? So if you ignore this one, what's left is these two terms, and bring it to the right hand side and divide it by 2m. What we get is this one. Okay? And this looks like familiar form of the in quantum mechanics, like a Schrödinger equation, but interpretation is a bit more subtle. Here, phi doesn't have phi is the operator. Discarded phi, or bar phi, or whatever you call it. So we treat this phi as an operator. What was it? This phi as an operator in the previous quantum history. So that's why we have the this part, because I mean in here you have a dagger expansion, and then we treat it as the operator. So therefore, this phi plus of t should be treated as an operator. Maybe I think instead of t, I should write down just x. And yeah, just x. And so therefore, this component of the phi should be also treated as an operator. So therefore, it's not wave function. Okay? So we want to make it a connect to a wave function in the following way. So here it looks like a Schrödinger equation. Look like Schrödinger equation, but phi of x is not a wave function. So to connect to the Schrödinger equation, we just take the following path. So to get this equation, we need the following Lagrangian. So we just introduce some conjugate field phi star, I call it phi dot, and then minus maybe I should write down like this way. seems like they finished the duty. So, yeah. So if you start this Lagrangian and take the equation motion, so then, so take a variation of phi star, and what we get is that the I times phi dot minus or plus 1/2m, right? And is equal to 0. So therefore, equation motion agree with this guy. Okay? So therefore, this Lagrangian can be understood, the Lagrangian for this equation motion. And then we go to the Hamilton formalism. If you have a question, please tell me. So to go to this Lagrangian formulation and go to Hamiltonian formulation, we introduce the momentum, conjugate momentum phi. So which is the it's just phi star. So therefore, the Hamiltonian is just a pi phi. Dot minus Lagrangian, which is equal to just the following form. And this is also a very familiar form for Hamiltonian in quantum mechanics. Okay. So the first term cancels with this term, and we have only special term for Hamiltonian. And then the wave function can be understood as follows. The wave function psi can be understood as the special integral to Q, and you introduce the wave function, and then x is the one particle state in the coordinate space. So this can be understood as state or like a general state or general wave function in the quantum mechanics, and we just want to act this Hamiltonian on this side, and we want to see what's going to happen. So that's what we want to do. Here, this psi of x is just an ordinary function of x. It's not operator. Okay? It's not operator. And this state I constructed last time. So if you forget about it, you can look it back the note or lecture note, or just watch the video. Okay, and then we want to act Hamiltonian here. To do that. Okay, let's act Hamiltonian on the side. And this is Hamiltonian density, so we need to integrate over all the special slice. So this is a Hamiltonian acts on the side. Okay. So that's how it acts. And now this phi, this Kali phi, still we treat it as an operator. So operator has the Fourier expansion, and we take only like a so time forwarded component. So therefore, what we pick is that the only this part of the integral we pick. AP e to the I. So this can be combined with this e to the minus I and t to get the e to the minus ip dot x in full integral. So e to the minus ip dot dot x can be understood as e to the minus I ep t plus ip spatial inner product. Okay? And this part will appear in over there, and the ep is just roughly speaking just mass. And this spatial inner product appears in Fourier integral. That's how you take the Fourier component phi x star is just a canonical conjugate, so therefore you have a AP dagger and the e to the minus I p. So we take the other component of the integral and you plug that into here, and then we'll see what's going to happen. So plug this Fourier expansion into here, and what we have is that the dqx what I'm doing here? I'm sorry, I just got confused. I think there's a typo in my lecture note. dqx is missing. Sorry. Cube, and then nabla acts on only this part, you get the I times p, and then nabla acts on this part, and you have a minus I dot p. So therefore, what we have is p square, p dot p over 2m AP dagger AP acts on psi. Okay, do you agree with that? So this nabla acts on this the e to the IP part and bring it, and the e to the IP counter each other. Okay. I mean, this part, strictly speaking, you have to treat P and this P, or you have to use Q indeed. Okay, Q indeed. but e to the IPX minus e to the IQX, Q integral will give delta function. So therefore, what's left is P integral. Strictly speaking, I just omit this part. I hope you guys understand.
Is there x?
Huh? Yeah, x integral here.
X integral should.
Oh, I see. X integral. Why?
The second line should be taken out.
Second line, it should be taken out. You're right. You're right. You're right. That's why the note is correct. Sorry. Note is correct. So to get the delta function dqx, you have to perform. Okay, and then the plug this wave function into here. What you get is spatial integral. Sorry. Thanks for correction. And then p squared 2m. And then AP dagger AP psi of x, and then to get the x state, you need to do the following operation. Okay, so then you just need to do the manipulation. I hope I can erase. Okay, let's go to here. Then we just use this following AP dot AP dagger is equal to delta function. So P and Q. P minus Q. Okay, and times I. So if you use this relation, this can be just swap this one. Then AP another 0, and what's left is this delta function. Okay, delta function. So therefore, what you have is that this one is equal to this one is equal to dqx dqp and 2 pi q e square over 2m AP dagger, and then e to the minus ip dot x and psi of x acts on 0. And then do that just integral apart. What you do is that this can be written as the 2p squared can be written as follows. I mean, it's very simple manipulations I'm doing. Minus 1 over 2m. Yeah, actually, strictly speaking.
I think there may be some problem about G.
I think here I should treat like Q
Right.
and Q and integral dq. Sorry. I think this is the correct way. So I'm very sorry. The election of this is, and then if you perform dq integral, that hits delta function, and what's left is this one. Sorry. The election is not correct. So this p square can be understood as e to the minus I p dot x and psi of x of c. Okay, and then just do the integral part. What we have is that the dqx dqp 2 pi of q e to the minus I p dot x minus over 2m delta squared psi. So now just integral parts, this nabla, sorry, not delta, nabla acts on psi twice. Do the integral parts and the AP. Okay, and do the p integral. It just give you the position one particle space in position space. So therefore, what we get is that the minus 1 over 2m nabla squared psi, and then position one particle state in position space. Okay. So this is it. So therefore, Hamiltonian acts on is really acting on like 1 over 2m nabla square acts on psi. Okay. So therefore, this is exactly the Schrodinger equation we want to have. This can be understood as the is equal to I nabla ddt psi. So this is exactly what we want. So now here psi is treated as a wave function. Instead here phi is treated as the operator. That's moving from operator to wave function. Okay, so this is how you connect the relativistic field theory to the quantum mechanics.
Wow, we have been last degrees of freedom in this number.
Because we throw away the one of the component, and also we take this limit. The Fourier integral has only one component, right? So in field theory you have the AP and the A dagger P, right? And we only take the time-divided one. with E tape. That's why.
Sir, I have a
Yes.
question.
Yes.
Then we can isolate the field components
Yep.
associated to this dynamics. What does this step mean?
Where are you pointing out in lecture note?
It's just under the 3.3 non-realistic limit. We can isolate the field components associated to this dynamics. So then we write 5 plus x equals to.
Yeah. So here you can take like the plus minus, right? You can take plus minus if you take the square root.
Yes.
And I pick only plus one. Energy is plus one. So therefore, I mean Fourier transformation. If you try to do the Fourier transformation, you have e to the minus I e p t or e to the plus I e p t. When you do the two part we have, but we only pick this part to go to non-realistic. That's what. That's why his question is also related to this one. So we throw away this part to go to non-realistic. Okay. Any other questions? Okay. Now, so we talk about the free scale theory, and we're moving on to the so-called fermatic theory, free fermatic theory, which is called Dirac theory. Okay, so now we are moving on to free Dirac theory. Free Dirac theory. Previous time, so spin of field is equivalent to representation of the SO Lorentz group 1.3. So that's what I meant. So how the Lorentz group acts on the field. For scalar field, phi of x is mapped to phi of just lambda inverse of x. But the gauge field or vector field, it acts like a lambda mu nu and nu lambda inverse of x. So that's how the act the Lorentz group, and we would like to understand how the Lorentz transformation acts on the fermatic field. So in general, so phi a, so indices a acts on like this. So in general, so the Lorentz group under Lorentz transformation, phi should transform like this way, and this is the action of the Lorentz group on the field, and this MAB determines the spin of the field. And then so we know this is spin 0 and spin 1. And we would like to understand how does it look like in spin 1/2. So how this MAB look like for spin 1/2 field? That's what we are going to learn from. Is it okay? So to do that, so we first need to understand the Lorentz re-algebra. I think more than half of students here are taking this the particle physics, right? The course of this Gu Jiayin's particle physics. I think he explained lots about the group theoretical aspect of quantum field theory now. So I'm not going to go into detail so much, but but we will review the so-called Lorentz-Lee algebra. Lorentz-Lee algebra. So Lorentz-Lee algebra, so we just have a group, and when you so we just write down like this way: e to the minus I over 2 omega rho sigma j rho sigma. Yeah. So we just write down like this way. I think you guys just learning SO. Anyway, I think in particle physics you guys have SU2 or SO3 and also Lorentz SO1.3 and so on. And then it has the group, Lie group, and the Lie algebra, which is the some infinitesimal transformation. If you just look at the infinitesimal transformation, you just see the relation for this generator J. So this is infinitesimal. This will generate the infinitesimal transformation. Then we like to see how this infinite transform generator will satisfy the relation. What kind of? And it turns out that we can just write down J mu alpha beta is I times G mu alpha. So I just give you the like this way. I just give you an example. So for instance, for rotation along z-axis or x3 axis, is just lambda mu nu. We learned that lambda mu nu is equal to 1 cos theta sine theta minus sine theta cos theta. And then 1, and the other is 0, the other. So this is the, and then if you take the, what's that, J, why do I write like this way? Oh, sorry, I think, okay, so I just write down, so this part, rho, sigma rho, J rho sigma, and that. So this is just parameter. It's corresponding to theta here. Okay? And then I just write down this J mu nu is equal to omega mu nu. Okay. Then this should satisfy. The following. So we know that the lambda mu nu, G mu nu, lambda mu rho, lambda mu sigma is equal to G rho sigma. Okay? And then, so therefore, this can be understood as the following. Maybe I should write down more precisely. Very sorry, I think I'm not well organized today. Good. So here we can just write down lambda mu nu, and we take this capital omega to be very small. Then what we can write down is delta mu nu minus I over 2 sorry, I think most likely I just need to. Sorry, I think. Okay, let me do that. Let me write down like this way, omega mu nu. And then, so therefore this one should be I over 2. Okay, then plug that one into here. So then for the G mu nu, delta mu rho plus omega mu rho, delta mu sigma plus omega mu sigma. It should be G rho sigma. Okay. So then you just take a look at the leading order of the variation. Therefore, here you just give you G rho sigma plus. So you just act G rho sigma is coming from this times this times this one. So now we look at the this times this one. Then what you get is omega mu nu. Sorry, rho sigma. So yeah. So what I'm doing here? Yeah. So I think you understand. Delta G mu nu delta nu sigma becomes delta mu rho mu nu, right? No, mu sigma, and the mu sigma would lower here and it becomes sigma. I think I should write down sigma rho. And then, so we just look at the this times this one. Then this one will give you rho sigma. Okay. And then you have a quadratic term, but order of omega square, but I'm going to ignore. And G rho sigma. So therefore, we just count out, and what you get is omega rho sigma should be equal to omega sigma rho. It should be anti-symmetric on the exchange of rho sigma. Do you understand what I mean? Is it okay? Are you following? Okay. Seems like not. So this times, this one will give you this time. Do you agree? Okay, then let's go to the next one. Use the red one. So this times this one. Okay. So then we just look at the G mu nu, omega mu rho, delta nu sigma. So this is red term is G mu nu, omega mu rho, delta nu sigma. Do you agree? So far it's okay. And then let's erase unknown part. So what we get is that the so this one will become, if you take a contraction nu, then what you get is mu sigma and the omega mu rho, right? Do you agree? If you take a contraction this one, then if you take a contraction mu, what we get? Oh, sorry. I think this is just G mu sigma. Okay, and this is equal to omega sigma rho. Do you agree? Is it okay? So just take contraction on nu, and then mu is swapped to sigma. Okay? And if you take contraction mu is lower than sigma. Okay? This is tensor calculation. And what you get is this term. And if you do that, the same thing for maybe blue, this one and this one and this one. What you get is this one. You just swap rho and sigma. Is it okay? Should I do the calculation? Okay, let me do it for you. G mu nu delta mu rho omega mu sigma is equal to what was that? G nu rho omega mu sigma, and if you take construction nu, you get the omega rho sigma. Is it okay? And you get the second term. Okay? This should be equal to G rho sigma. Therefore, they cancel, and you can ignore omega square term. This should be equal. This should be equal to 0. Okay? Therefore, you get this one. So it should be anti-symmetric under the term. Okay? I hope you guys are following. Okay. So then, if you write down this one is equal to delta mu nu plus omega mu nu. Okay? Omega mu nu. Then we can just write down. So this can be understood as essentially e to the omega mu nu. E to the omega mu nu. Then I pick omega mu nu as the 0. Maybe I should write down like this way. Okay. So I pick like this way. Is it okay? And then just do the e to the omega mu nu is equal to delta mu nu plus omega mu nu, and just do the Fourier expansion. No, Taylor expansion. Omega, whatever, mu sigma omega rho nu, and 1/2, and just Taylor expansion, right? You know, right? And dot dot dot. This is, e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial, and dot dot dot. It's the same thing. Okay. Okay. And I'm going to erase it. I'm going to erase. Do you agree with this point at this moment? And this one is delta mu nu is just a 1, 1, 1, 1. And next is theta minus theta, and the rest of the is. And next is this one, and this is equal to 0. 0 and theta. You have to distinguish theta squared. I think I'm probably correct. Minus. Is it okay? And 0. And 1/2. Do you agree? And next is, as you can easily imagine, this is equal to 1/3 factorial. And then I think this should be theta cube minus theta cube 0, 0, like this way. Do you agree? So what you end up with the, so if you do the everything, 1, and then here you have the Taylor expansion, this one. So 1 plus whatever, minus theta squared over 2 plus 4 factorial of theta to the 4th dot in 2, 2 component, which is cosine theta, right? And then here you have minus theta plus 3 factorial theta cubed dot, which is minus sine theta. Okay? Taylor expansion minus sine theta. And here you have a theta minus theta cubed 3 factorial plus dot. And here 1 minus theta squared over 2 plus theta 4 factorial and dot. And 1. Do you agree? Do you understand what I'm doing?
Yeah.
Okay. So therefore, it just gives you the Taylor. So if you plug this one into the e to the omega, if you put an exponent to the e, so what you get is this one. Just give you the Fourier expansion of this rotation. Okay? So therefore, this omega mu nu can be understood the infinitesimal transformation of this rotation. So this is what I meant in here. So similarly, we can do the same thing for Lorentz boost. Lorentz boost is essentially log mu is the cosh beta sinh beta sinh beta cosh beta zero, zero, zero. So this is a Lorentz boost along the x1 direction. On the x1 direction. I forgot beta is called rapidity. I forgot the name in English, sorry. I should have known, but you should look at the Wikipedia. I think rapidity, I forgot. Beta is called rapidity, right? And then, so therefore, as you can easily imagine, omega mu nu, you should take the zero, beta, beta, zero, and big O, like this. Okay. Then do the same thing. E to the omega mu nu, mu nu is equal to, just give you a full expansion, 1 plus beta square over 2 plus beta cube, for factorial. And here you have beta plus beta cube 3 factorial plus dot dot dot. The same thing. 3 factorial plus dot 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 1 plus beta square over 2 plus beta 4 over 4 factorial dot dot dot. And then 0, 0, and 1. Do you understand what I'm doing here? Okay, good. So therefore, so leading term, we just take the leading. If you take only look at the leading term, beta only here, this part is survived. But if you put it into the exponent, you can reproduce this Lorentz boost. Okay. So that's why this generated. This is the infinitesimal transformation or Lorentz boost. Can be understood. Do you agree? I hope you understand that. So, and if you combine everything together, you can just check that this is a transformation. This capital omega, this capital omega can be understood as the theta or beta, okay? Theta or beta. On the other hand, this general sigma mu nu can be understood as the component. So if you get rid of beta, it becomes 0, 1, 1, 0, like this, right? Like this. So this part can be understood as the J rho sigma mu. That's what's happening. And you can check really, if you use this one and plug that into there, omega mu nu will satisfy, will become like this way for Lorentz boost and the rotation. It's just and you might wonder, so this should be symmetric anti-symmetric under exchange of rho and sigma. But this doesn't, yeah, okay, so this looks like a anti-symmetric under exchange of mu and nu, but here it's not, it doesn't look like so, right? But however, if you try to move mu to the upwards, so here it's both are down indices, lower indices, upper indices. So here, if you try to, so maybe it depends on how you notation. I don't know which one. I would take which way. I think this mu is equal to 1, 2, 3, 4, and here nu is equal to 1, 2, 3, 4. No, 1, 2, 3, 4, 0. Sorry, 0, 1, 2, 3. Sorry. 0, 1, 2, 3. And then, so therefore, if you try to move, for instance, mu downstairs, so this component, mu is 1, you get the minus sign, right? you get the minus sign to try to bring mu to downstairs. Because we take the 1 minus 1 minus 1 minus 1. You have to multiply this g mu nu to bring mu downstairs. Okay? So therefore, this component get the minus sign. Okay? On the other hand, here mu is equal to 0. So therefore, it's plus sign. Okay? So therefore, if you bring this intersection lower, it becomes anti-symmetry. But here, in this case, both mu and nu are the spatial. So therefore, it's not affected. So therefore, this anti-symmetry condition will be satisfied. Do you agree?
Yes.
Okay. Let me give you the Lie algebra. Where should I erase? I can erase it. So the Lie algebra, so this J mu nu can be understood as the follows. So rotation. So what you learned in the quantum mechanics is the angular momentum is like this way. Okay, and this. So to make it quantum mechanical operator, you just replace by x times nabla minus I plus I. Is it I? Forgot minus I. Forgot minus I. Okay. Thank you very much. I'm not careful. So the P just replaced by minus nabla. So therefore, this can be understood, Li can be understood as an epsilon ijk xj, and then like this way, So in particular, if you look at the L3 is just x1. I think I should be careful about the indices. Maybe this one is more convenient. Like this way, okay? So this becomes the operator of the angular momentum. We can do the same thing for relativistic case. Relativistic case, so this J mu nu, unfortunately there's something noisy stuff going on. So this J mu nu can be understood as the infinitesimal rotation. So this can be understood as the generator of the Lorentz transformation. Therefore, I can write down like this way. In particular, if you pick mu and nu as a 1, 2, it becomes a rotation. Okay, rotation along 3 axes, which is just exactly the same as this guy. This guy. But if you pick mu nu as a 0 and 1, then you get exactly this generator. So. And it's a good exercise that to do this one will satisfy the following commutation relation. Is equal to I G mu sigma too many, sorry. My brain's not working, sorry. Okay, so this will be satisfied.
In the first
There's a
phrase,
typo.
Thank you very much. That's very easy to check. Just plug that into here and do the
There's a typo. The present term J new name, not the J new sum. That's right.
where?
The first term
This is
on the left.
on the left.
on the left. Oh, okay.
First term.
Okay. Thank you very much. Thank you very much. I will correct it in the later. So this one you can easily check. Just plug that one into here. Do the. Should I do that a little bit? Okay. So let me do. I'm not gonna do everything. But the point is that plug that one into here. You get the x new. So this one minus plus the opposite. Okay, so this is equal to this one, right? And then literally do that. What's the eraser? Just computer generation. I mean, just do the honest calculation. Unfortunately, you have to do that. Okay. For instance, let's get the one term. Let's get the one term. This one. The rest is the same procedure. So to get this term, so this one should act on this one, right? So therefore, so let's look at this part. Okay, and then. Yeah, I think then I think what we need to look at is this one. Okay. So let's take a look. So if this one acts on this guy, then what you have is minus minus minus, which means minus x nu. So g mu sigma. This one acts on this guy. You get the g mu sigma and the x nu partial rho. Okay, that's what we get. And if this guy acts on this guy, again you get the g mu sigma. But now we have a plus sign, and plus sign. So therefore this one is the essentially minus x rho x nu, right? Okay, do you agree? Are you following? Is it okay? So here, so this guy acts on x sigma, then you get the g mu sigma. Okay? What's left is x nu and then del rho. The same thing here. This guy acts on x mu will give you g mu sigma. Okay? Then what's left is x rho and then del mu. And you get this, be careful of a sign, this one. And this is exactly equal to I times g mu sigma j mu rho. Okay? And that's how we get this term. And the rest of the term should be how it acts and how we take a combination. Okay? Is it okay? That's how you get this algebra of the Lorentz relation of Lorentz the algebra. Any question at this moment? Okay, then let's take a break for 10 or 15 minutes, and then please do not walk here. Please walk out back side, and then if you Want to submit the homework directly, just submit it here. Okay. Let's take a few minutes.
I have a question about the carry out the action on the state vector. So this is one part of the state vector.
No, it's a superposition of the size. It's not the one particle system. It's just a superposition of one particle.
So what is this QFT? That will be called the dual of one particle.
Yes.
Okay, so what we do is that depends on the
Yeah, of course.
So we have to choose this specific 5-star file to get the Schrodinger series.
That's true.
So I'm kind of feeling weird about the physical interpretation. So how does this file fit into the probability of what must be
What? I mean, this is the problem. This function should be the problem. This should be not the problem.
Special case, two-dimensional special case, right? And we want to not as a four-dimensional three-time space. That's all one thread. So what this for? I know before is SO4. I can send it, but SO1 squared is second is 1 minus 1 minus 1 minus 1. So here
But then if it's so full, this becomes delta instead of GB. So this take care of it. This can take care of one thing. So the metric. So that's the difference in SO4 and SO1, 3. So this index is natural and take care of this sign issue. Some questions?
I don't know why this relation. I always find there should be a one sign. I don't know whether it's exactly. I don't know why there is only one sign. So we should do this instead of this.
I'm sorry?
For example, let's add on any x alpha. We get this. Then we can get this relation. But it shouldn't be the Einstein here to get this relation.
I'm not careful about sign. You get if you have a minus and minus, they get plus. They get minus and they have a minus.
From this relation, we cannot get this relation. There is another side.
Okay, I don't know. I'm not careful about it. I have to check. Right answer question. Yeah, of course. PDF. As a homework can be submitted via e-learning, just attach PDF file to the e-learning. That's also fine. That's totally fine.
I don't know how we can write 5 plus is equal to either for an IMT. That's the economic outcome.
The plane wave equation, I mean,
It's not the Python equation, but
no, I mean, so there's a two solutions. So one is phi of x e to the minus I e of x. And then some and some constant or other solution e to the I p of x. And I pick only this. Yeah, four momentum. And this can be understood as and then I only pick this for 5. That's what I need.
So, and what is the fact?
Maybe I just put 5.
So this is the solution of the regulation.
Yeah. Or more precisely, this phi should satisfy phi. The momentum dependence only appears in the I mean, here, dependence is a relativistic non-relativistic operator. So therefore, I mean, dt should be much less than I mean, all the time dependence only just Here you just take the 100 on both sides. Okay.
Maybe we can think of this like the placement. This is the probability, and this is
But even without duration, should why not run this? The longer the edge should be very much the M should be treated much bigger object than any energy. C squared should be less than any energy, whatever, any potential, whatever. I mean, stuff square and so whatever, the energy. All should be much smaller.
Should be the
Yeah.
just
type. I should write down beta or theta or what. It's just parameter.
and beta is equal v c v divide c or just m.
Means the rapidity.
Yeah, rapidity. I already forgot the formula. Well, what's a gamma? So gamma is equal to 1 b squared. Then, so this we treat this one is equal to wash. So I don't think beta and beta will be really way. Rapidity. It's really rapidity. I can do it. I Okay. So let me move on. Okay, so this is what we introduced the Lorentz algebra, and we want to do something, create some representation of Lorentz algebra. So this is the one I erased already. M is representation of a Lie algebra. And unfortunately, I cannot bring it out. Oh gosh. Okay, so the phi A is mapped to an AB lambda phi B of lambda inverse of x, and we just write down this one is the sum e to the whatever minus I over 2 like this one. We want to write down, and this representation S should satisfy this this relation. That's what we are going to construct. How this matrix S can be constructed. That's what I'm going to construct. Yeah. And then hopefully camera is okay, I think. Okay, so to this end we introduce so-called crippled algebra. So introduce the 4x4 matrix. Anyway, any matrix is okay, but now it's just a 4x4 matrix. Matrices so for gamma, the mu runs for 0 to 3, and then we satisfy the following relation: gamma mu. If you take an anti-commutator and you have a 2 times d mu times 1, and this is 4x4. That's what I want. Do you understand? So the algebra means you have addition and then multiplication. And this multiplication is given by this anti-commutator. That's what you mean the algebra. And in particular, I can take the following. So this is called crippled algebra. So algebra means multiplication. So this is Lie algebra. Lie algebra has to have an addition and a multiplication. So addition is just as a matrix. As a matrix you can add, but multiplication is just not ordinary multiplication. So if you have a matrix A times B, A, and matrix B, usual multiplication is something like this one. Okay? But here we define the multiplication. Let's call multiplication B as minus B. This is a rule. Okay, so we define multiplication as like this way. That's a Lie algebra. Okay, so that's a rule for multiplication. We define like this way. So this dot is ordinary multiplication. Ordinary multiplication as a matrix. matrices. But in Lie algebra, this is not a multiplication. Lie algebra is just a multiplication should be commutator of the matrices. Likewise, cripple algebra, multiplication, if you have a 4x4 matrix, 4x4 matrix, multiplication is a rule. As a rule, we take like this. Anti-computational relation. As a rule. So this is the ordinary matrix multiplication. But that is not the multiplication inside the crippled algebra. We define multiplication inside the crippled algebra as an anti-commutative. That's the rule in crippled algebra. The addition is just an addition as a matrix. So A plus B is just an A plus B as a matrix. Just add entry. As an entry. You understand what I mean? So that's why it's called crippled algebra. So multiplication is the rule, as a take of anti-commutative. And we can take if you take this like this way, gamma I is the minus sigma I. Minus sigma I. In this lecture, we take like this way. Sigma I is a power matrix. So let's check. It's super easy. I mean, okay. Gamma I, commutator of gamma I is just a 2 gamma I square, right? And this is 2 times minus sigma I square. And B, sigma I square. And this is equal to, we know sigma I square is equal to identity, right? Is it okay? Sigma 1 is 1, 1. Sigma 2 is I. Sigma 3 is 1 minus 1. Okay? So if you, the square is always 1, right? This is, so therefore this is 2 times identity. Okay? 2 by 2 matrix. And GII is minus, right? Minus 2 times identity operator. That's what it means. On the other hand, if you take the, for instance, this stuff. Gamma 0, gamma I, if you take a commutator of this one, what we get is that minus I do you understand? So this is equal to gamma naught gamma I, gamma naught. Okay? Are you following? So therefore this is 0. So this, since 2 times z0I is equal to 0, so that's how it's consistent. Okay? Do you agree? Like this way. Okay. So then we are going to introduce the so-called S matrix. Sorry, I shouldn't say S matrix. S matrix appear in the other context. So some matrix which is a commutator of gamma mu. so I define S rho sigma is I over 4, which is gamma rho, gamma sigma is equal to 0, and then I over 2 gamma rho gamma sigma when rho is not equal to sigma is equal to sigma, sorry. Rho is not equal to sigma. Okay. So the formal one is super, of course it's easy to see, right? It's an anti-commutator, so it becomes 0, of course. On the other hand, this one is it okay? Do you agree? Since if rho is not equal to sigma, we know by definition gamma rho, gamma sigma plus gamma sigma, gamma rho should be equal to 0 by definition, because it's off diagonal. What was that? Off diagonal G mu, off diagonal entry. Therefore, if you gamma sigma gamma rho should be minus gamma rho gamma sigma. So if you take anti-commutator here, you just add them out. Okay, so therefore this can be written. So this can be written as the maybe I should erase. Some people are still taking notes. Diligent students are taking notes, so maybe. Like this one. So which indeed satisfied if rho and sigma are equal, it becomes G rho sigma times identity times 2. Okay? So therefore, if you take 1 over 2, you cancel each other. So on the other hand, if rho is not equal to sigma, this is 0. This is 0, so it just nails it. Okay. So then now, so we just look at the following, the computational relation of the. So then now we have over 2. Okay, by definition, okay. So by definition, and we plug into some component. So here I will add something nice one. Here I will add. Here is the, I think the gamma mu. Gamma mu rho, right? Sorry, gamma rho nu. At the plus I over 2 minus I over 2 gamma mu gamma rho gamma mu. Okay. I just do that, and then take combination of this guy. So they cancel, of course. I just add and subtract. It's just 0, right? And then take this guy and apply the Crufeld algebra over there. Okay. So nu rho plus rho nu is equal to 2 times G 2 times metric G nu rho. This is equal to so this is equal to I times gamma mu G nu rho, because we take the anti-commutator of gamma nu, gamma rho. Here we take anti-commutator gamma rho and gamma mu. Okay? And if we have careful about sign, so what's left is gamma nu and G mu rho. Okay. And then unfortunately I erased. Did I erase? Erased. I think I erased. So plug what was it? J mu alpha beta is I. G mu alpha. G beta. Minus G mu beta. G mu alpha. Plug that into here. This can be understood as the minus J mu rho sigma gamma. That's you can easily check. So if you take a commutator of S and gamma, Lorentz-Lee algebra acts on the gamma matrix as a vector. Do you understand what I mean? So this sigma, so as I mentioned, so A mu is transformed as a gamma mu, gamma mu nu A nu lambda inverse x. So here lambda acts on A as a vector. Okay, 4 vector. Likewise, this J mu nu, so this can be understood as I mentioned many times, delta mu nu minus I over 2 sigma rho sigma J rho sigma mu nu. Okay? So this J can act on this 4 vector mu as a 4 vector. Rho sigma sigma. This is also 4 vector. So therefore, if you take a commutator of S and gamma, somehow magically the Lorentz-Lee algebra acts on gamma as a vector. So that's some very, very miraculous property. And I'm going to do the following thing. So I will surprise you a bit more. If you take a commutator of this one, okay, I over 2 S mu nu gamma rho gamma sigma. Okay, and we know that the A, B, C. If you take this one, you get the A, B, C is equal to C. Plus S. Do you agree? Or you don't agree? Do you agree? So we use this factor. So here S can be treated A, and B, C is gamma rho and gamma sigma, right? And we can apply this one. We know AB can be AB relation can be used this one. Okay? Do you understand what I mean? Therefore, this can be understood. Minus 1 over 2, and then so again, so you can apply gamma mu nu gamma rho, so we get which one? This one. So therefore, I cancel I times I, we get the minus 1, and the gamma mu gamma G nu sigma minus gamma nu G mu rho times what was it? Gamma sigma. Okay. So this finish this part. So when you submit the paper, please use stapler to otherwise this comes. So please use stapler to when you submit the homework. Otherwise It will be like this. And some, if I lost 1 page, your grade will be lost 1 page. So, okay. Anyway. Anyway, I finished this part, and next is this one. Just change rho to sigma, so therefore this one is equal to sigma gamma mu G mu sigma minus gamma mu G mu sigma. Do you agree? Do you agree? So far, are you following? Is it okay? Some students doesn't look like okay. Okay, maybe I should explain. So this is equal to AB minus BAC, and then plus BAC minus BCA. And if you counter each other, what's left is ABC and BCA, right? So this is exactly the definition of this one, okay? And what I did is that the first, you treat A as a S mu nu, B as gamma rho, and gamma sigma as a C, okay? And you first apply this one here, then you get this one. So this is commutator. Okay, anyway, so you guys just do this kind of computation by yourself. I'm not kind enough to show everything. AC. Okay, and this is equal to C, and this is equal to C. Yeah, actually, I'm a bit strong today. So, and then just do manipulation. Manipulation, so what you get is the I times G mu rho. And we know that the, what was that? We use this, this relation, gamma rho sigma, can be understood as the minus I over 2G rho sigma as an S rho. So then we have S mu sigma minus gamma mu gamma sigma S sigma minus G sigma S rho plus G sigma S mu. So this is what you get if you use this relation, and plug that into here. Okay. And now, comparing with the, did I preserve? Unfortunately, no. So this is exactly the relation of Roman algebra. So if you replace S by J, this is exactly what I have written before. By using this, so I have written here, right? Oh, there is a, here it is. What's left is here. So just compare between this guy and this guy. You can see exactly the equal. Okay. Exactly equal. So if you take a commutator of this S matrix, starting from triple algebra, and define S like this way, okay, and take commutator, and what you get the relation of Lorentz algebra. So it's a very, very magical sign that the somehow triple algebra is they can construct the action or representation of Lorentz algebra. And I'm going to erase here. Anyway, you already saw it. So therefore, we can treat this S matrix as the representation of Lorentz algebra, so that we can just consider the following thing. If you construct a field that transforms the so if you introduce field psi alpha of x, that transform under the Lorentz transformation is e to the minus I over 2 omega rho sigma s rho sigma. Okay. S rho sigma acts on psi. So alpha, beta, psi, beta, alpha. So recall that this each S mu nu is a 4x4 matrix. Okay? So because S mu nu and S rho sigma is just a matrix. Oh, okay. So more precisely speaking, I should introduce the identity 4x4 matrix. Okay. So the G mu is 0 sigma is just number, but this guy is 4x4 matrix. So precisely speaking, you have to introduce 4x4 identity matrix. And this gamma matrix 4x4 matrix, 4x4 matrix. So then you multiply together. So there's 4x4 matrix. And it's an identity operator, identity 4x4 matrix. So this S rho sigma is a 4x4 matrix. These indices appear as alpha and beta, as a 4x4 matrix. Okay? And rho and sigma is just how you anyway, so rho and sigma just run 0, 1, 2, 3. And depending on how you pick rho and sigma, the content of this S, the 4x4 matrix would change. Okay? That already we saw for Lorentz transformation, right? So sometimes whatever omega mu nu can be written as like 0, 0, minus 1, 1, 0, 0. If you pick mu and nu are no, this is the omega rho sigma j rho sigma some number, right? Mu. And here rho and sigma is just should be 1 and 2. Should be 1 and 2. Rho and sigma should be 1 and 2. On the other hand, if you pick rho and sigma is 0 and 1, it becomes something like 1, 1, 0, 0, 0, 0, 0, right? Like this. Therefore, if you pick different rho and sigma, the 4x4 matrix will change. That's easy to see from here, right? Easy to see from here. Anyway, so we define the field that transform under Lorentz transform like this way. And I call it this one is S lambda. Okay. And we just take a look at so for rotation, we need to take the spatial. So this is I over 2 gamma, or maybe KL. KL is equal to 1/2 epsilon KL m sigma m 0. So this is an easy calculation. I mean, here I use a basis for this one, gamma I and the gamma K and gamma L. So we take this basis, then you get this one. Okay? That's easy to see from power metrics. Okay? Coming from power metrics. Do you want me to show that? I mean, it's super easy, right? I mean, for instance, if you take the case 1, 2, so gamma 1, gamma 2 is equal to sigma 1 minus sigma 1, and sigma 2 minus sigma 2, minus sigma 2, sigma 2. Okay? And if you multiply them together, so gamma 1 times gamma 2 will give you doing something wrong, and I here, so give you I think minus I times sigma 3. Okay, minus I times sigma 3. So therefore you get this one is equal to minus I times sigma 3, sigma 3. That's super easy to check. Okay. That's already you learned. So therefore, if you look at the rotational component of this S matrix from Krupal algebra, you get this matrix. And then if you exponentiate S of lambda for this guy, exponentiate e to the what was that? Minus I over 2 gamma KL SKL, and this is equal to e to the minus I phi and sigma over 2, and e to the minus I phi and sigma over 2, and 0, 0. So therefore, so this psi field, it transforms like as you already seen in quantum mechanics. In quantum mechanics, if you do the rotation of the spin up and down, so you get this factor, rotation. So that's what you learn in quantum mechanics. Okay? So I think the particle physics course, this will be the generator of the SU2. Okay, rotation. I think that's how you learn. How you learn SU2 in Gu-Ja's course, I guess. So therefore, this rotation will rotate spin and spin down. Okay, that's what we already know. Therefore, this psi is somehow related to spin 1/2 field. That you can easily see from here. And fortunately, I can erase this part. So introducing this crippled algebra, somehow you can construct the Lie algebra, representation of the Lorentz Lie algebra, and somehow you get the spin 1/2 here. It's very magical, but we should appreciate it. Okay, so now we look at the Lorentz-Booth part. So Lorentz-Booth part is essentially S0 phi, and this is, I mean, you just follow the computation of this one I over 2 gamma 0 gamma maybe I call J gamma J, and this is equal to I over 2 minus sigma I and sigma I, 0, 0. And here, so if you exponentiate e to the minus I over 2 gamma 0 I j and s0 j, and what we get is s of lambda is equal to e to the minus I over sigma, and then over 2, and they started again. Oh, come on. Okay. And this is new phenomena you encounter in relativistic case. In quantum mechanics, you don't see how the spin up and spin down field is transformed under the Lorentz boost, but here somehow upper two component and lower two component is transformed differently. Okay? One is minus this. Oh, sorry. Maybe I should say this dj ij. I just parameter the difference. So this alpha runs for 1, 2, 3, 4. Now I'm not gonna use 0, 1, 2, 3. Okay, because this alpha is really not the 4 vector coming from the Lorentz space. This alpha is not this is, be careful, not Lorentz indices. Be careful. So since we know that this S rho sigma is a 4x4 matrix, okay? 4x4 matrix. So therefore, 4x4 matrix, okay, we pick S, for instance, K and L is a spatial. It's a 4x4 matrix like this, right? Like this. So therefore, S acts as psi 1, psi 2, psi 3, and psi 4, like this. Okay? And these 4 component is just a 4 vector. It's not the Lorentz 4 vector. It's just a vector which received action of the Lorentz representation Lorentz loop. Be a gamma matrix or be a critical algebra. Okay. So therefore, be careful about this alpha. It's not the so this is has a component alpha and beta. This 4x4 matrix alpha beta is really 4x4 matrix alpha beta. This 4x4 matrix written here. Okay. And choice on K and L appear in this combination. Hopefully you understand. Okay. So therefore, the psi field receive the action of the Lorentz group, and we want to construct Lorentz invariant action by using this psi field from now. And that's the goal of this lecture. And then I think I need to do it. So I have 25 minutes. I think I can reach there. Okay. So we treat this gamma matrix is the, as I mentioned. So I already erased gamma is the 0, 1, 1, 0, and the gamma I is equal to sigma I minus sigma I. And we know that the sigma, the power metric has imaginary entries. So therefore, psi should be imaginary. Okay, we should treat psi, this field, as a complex field. Okay, because otherwise it doesn't make any sense. Because here I appears, and also sigma has an I component. Therefore, this is complex matrix. And the vector which receives the action of complex matrix should be complex. So in the previous lectures on the homework you did, the previous scalar field I just used this one is a real field, free scalar. Is a real field. Phi as a real field, but in the homework you guys just did the complex scalar in the homework. So likewise, we should treat this psi as a complex, okay? Complex field. But however, it received a different action of the Lorentz group than from the scalar, complex scalar field. So in complex field, we need to add a star here, and we just consider star, and it's a combination of the complex. So we just want to construct the Lagrangian using psi in such a way that everything Lorentz invariant from now. So to this end, we just introduced the complex conjugate. 他们短短许许短短。So a dagger so we introduce dagger as like this way. Okay. And this one is transformed under the Ross transformation lambda inverse of x as dagger of lambda. Okay, and then we'd like to ask a question: is this Lorentz invariant? Is this Lorentz invariant or not? So under the transformation, this one is S of lambda. Like this way. It transforms like this. So like this way. And to become, if it is Lorentz invariant, it should be equal to 1. Okay? So that therefore, in order for this term to be Lorentz invariant, S needs to be unitary. Yeah, it should be unitary, which means that the S dagger is equal to S inverse. This means unitary. But on the other hand, if you look at the definition of the S gamma, S dagger of lambda. Okay, I think my note is incomplete. E to the minus I over 2. My note is some block typo. And dagger, which is the E to the I over 2 omega rho sigma S rho sigma dagger. Okay. So therefore, in order for the this to be unitary, S rho sigma dagger. If it is question, the question is rho sigma. Since there is no minus sign here, if this is the case, this holds. Okay. But however, we know the so S rho sigma, if you just you can just check the explicit construction. S rho sigma dagger is just I times over 4 and a gamma rho dagger and a gamma sigma dagger. And then so I'm sorry, I'm very sorry. So this should be called Hermitian. Anti-Hermitian. Yeah. So anti-Hermitian means that the eigenvalue should be purely imaginary, right? Yeah, purely imaginary. Wait. How much?
There should be a minus.
No. It's a Hermitian. It's a Hermitian. Sorry, it's Hermitian. It's Hermitian because I mean it's a, so the eigenvalue should be purely real. Okay, it's real. It's called Hermitian. Sorry. Yeah. So therefore, but however, we know the gamma zero square is equal to 1, but on the other gamma I square should be minus 1. So therefore, eigenvalue of gamma special is the really purely imaginary, and this is real. Okay. If you take a combination 0i, it cannot be the Hermitian because it's an eigenvalue should be purely imaginary. Therefore, this is not the case. Therefore, this is not the case, and this is not the case. Okay? Therefore, dagger gamma is not the Lorentz invariant. But however, we can do the following thing. So that again, subtle difference appears subtle difference appear when you take combination of 0 and time and the spatial component. Because this is real eigenvalue, this is purely imaginary eigenvalue. If you take a combination 0 and I, so the eigenvalues become purely imaginary. Okay? On the other hand, if you take the both spatial part, the eigenvalue should be okay. The purely just real, it becomes real. So therefore, the difference between so what we need to compensate is the combination of 0 and I. Okay. So to make up for this gap, we introduce we just consider the following thing. We just need to notice the So this is Hermitian. This is anti-Hermitian. So therefore, we just notice that the following thing. So here you can easily check the computation. So here 1 1 sigma I. I'm running out of time. Sorry. 1 1. And then what we have is that this one is equal to just swap the sign. Okay. Swap the sign. Yeah. And then as you can easily see, this is equal to this is equal to this one, and this is equal to this one. Can you see that easily? Is it okay? For instance, it's very illuminating. If you take I is equal to 3, it's just a diagonal, right? Diagonal. So you just swap them by transform. Okay. So you just notice that this one. So therefore, from by definition, S mu nu and dagger can be understood as the gamma 0 S mu nu gamma 0. So therefore, if you take the exponent, we have is the S lambda dagger is equal to gamma 0 S gamma inverse gamma 0. So do you see that? Do you see this relation? So if you plug this one into here, gamma 0 is always, if you square it, it's just 1. So therefore, gamma 0 just appear in left and right. And on the other hand, you have a dagger, so therefore you get the minus sign and the plus sign, and the S stay as it is. So therefore, you get the minus sign here. Okay, so you can just easily check this relation, and what we have is that the so therefore, if you combine, so if you look at if you define bar as gamma dagger gamma 0, then this is transformed as follows. Under transformation or Lorentz transformation, gamma dagger S lambda dagger gamma 0, and this is equal to gamma dagger, no, psi dagger and gamma 0 S lambda inverse, and this is equal to psi bar S gamma inverse. This is exactly what we want. Now, as you know, so we already mapped like gamma 0 from right. We get the S dagger times gamma naught. On the other hand, you have a gamma naught times S inverse. And then we know that the gamma dagger, psi dagger and the gamma naught is psi bar. So we just define like this way. So therefore, what we have is if you have psi bar psi, and then under the Lorentz transformation, this becomes psi. And this is equal to psi bar. So therefore it's a long sigma. So this is very, very nice property. So this psi bar plays a very important role. And then, so we are going to do the following thing. And in previous time, so we checked that this S matrix define we check this one. And if you exponentiate this relation, so we can just have the following relation. So therefore, this means that the S inverse of lambda, the gamma rho S of gamma is equal to can you see that? Can you see this relation? So we know that this one is equal to e to the I over 2 omega rho sigma S rho sigma. So this is the case, and the gamma rho, and then here we take mu nu, and then gamma rho on the alphabet rho, and then e to the I over 2 minus omega rho sigma S rho sigma. So this is the case, and this is left hand side. And if you take right hand side, it should be e to the I over 2 minus j. Rho sigma j rho sigma that acts on mu nu as a gamma. And take leading order of so leading order of O omega. If you take this one, then from here what you get is that the 1 minus plus I over 2 omega s. I will be being schematic. Here 1 minus I over 2 omega s. Okay. So this is leading order. If you take leading order omega, then what you get is that the essentially I over 2 omega. I over 2 omega and S gamma. Okay, S gamma. And then here, if you take the commutator of the gamma times S, gamma S. Okay. So this is exactly the commutator of S and gamma, right? Do you realize? Okay. And if you look at this one, if you take a leading order, unfortunately, some sign mistake is short. Oh, no, it's okay. Minus j. Okay, I think the indices are strange, but yeah, I'm sorry. I think the index is very strange. I think I should hear rho sigma. Sorry. I think. I'm very sorry. I think I should use mu nu, and mu nu. I'm sorry, I made this mistake. It's crucial. Mu nu and mu nu, rho sigma, and rho sigma, and then this one is mu nu, rho sigma acts on gamma. Okay. So therefore, you reproduce this relation. Okay. So therefore, this is this relation If you take infinitesimal relation, you get this one. Okay? Do you understand? So therefore, if you sandwich by this Lorentz transformation of S, sandwich this gamma matrix by S transformation, what you get is a Lorentz transformation as a 4 vector in Lorentz 4 vector. Okay? You understand what I mean? So therefore, what we have is a very fantastic thing. If you have only 5 minutes left. If you have S of gamma, psi bar and Persian mu and gamma mu, let's consider this combination. Okay. If you take this combination, it is under Lorentz transformation, you have S of gamma inverse coming from here, and then you have gamma mu, and then S of gamma acts and partial mu acts on. So gamma mu acts on psi, but so this one is also transformed under Lorentz transformation. So this one is this act as the. How did I write this one? I already forgot how I write, but it's transformed like this way. Okay. Okay. And we know this one is equal to. So this one is equal to this one. So therefore, this is psi bar lambda mu rho gamma rho. So gamma rho and gamma mu sin mu. Okay. And if you take a contract of mu and mu, what you get is delta rho. So this is equal to psi bar delta rho mu. Delta rho mu gamma rho and mu psi. So therefore this is equal to psi bar gamma rho. So therefore it's Lorentz invariant. Okay, do you agree? Sorry, I think I should write down like this thing. Sorry, gamma mu. Do you agree? Do you understand what I'm doing here? So if you take S inverse S, if you sandwich gamma by S matrix, okay, then we have Lorentz transformation like this way. So this part, I'm sorry, just a moment, let me finish first. We can treat it later. So this part is transformed like this way. On the other hand, this and then on the other hand, this part is transformed under Lorentz function like this way. Okay. And if you contrast the gamma matrix, it's just the inverse matrix. So therefore you get the delta. Okay. And what you get is the original combination gamma dot nabla or delta. Therefore this is Lorentz invariant. And Lagrangian, so therefore Lagrangian psi bar gamma mu is indeed equal to is indeed the Lorentz invariant. So we know that the I think I should put the I here for the sake of it. So we know that the psi bar psi is Lorentz invariant, and you get this one, this term, and then here you get the Lorentz invariant part, and we just combine them together. And this is called the Lagrangian. Okay. This is called the Lagrangian. And then Euler Lagrange equation is very simple. If you take a partition psi, what we get is the I gamma mu psi mu minus m x on psi of x is equal to 3. So this is called Dirac equation. And then, so let me give you that. So this Dirac equation can be understood as square root of Klein-Golden equation. So if you combine so this is Dirac equation, you add another piece of the gamma mu psi mu minus m. So be careful of a sign here, and then I gamma mu psi. Then, so this can be understood as a gamma mu psi mu, because of sign difference, the first order derivative cancel each other. So what we get is m square acts on psi. Okay? Acts on psi. And we know that from critical algebra, this is just equal to 1/2 gamma mu partial mu plus m squared. Okay. So therefore, if you plug that into here, what we get is psi, and what we get is equal to partial mu plus m squared psi, and this should be equal to 0. And this is Klein-Golden equation. So therefore, starting from Dirac equation, add another piece of the same operator, just changing the sign here, you get the Klein-Golden equation. So therefore, Dirac equation can be understood as a square root of the Klein-Golden equation. Okay, I think it's a good place to stop. Let's stop here, and then, yeah, we'll meet next week.